On this problem, I have food and clothing are shipped to victims of a natural disaster. Each carton of food will feed 14 people, while each carton of clothing will help 6 people. Each 20 cubic foot box of food weighs 40 pounds, and each 5 cubic foot box of clothing weighs 20 pounds. The commercial carriers transporting food and clothing are bound by the following constraints. We have a weight constraint, and if you're taking a trip on an airplane, you know that there are weight limits on your luggage. So the weight of the airplane cannot exceed 23,000 pounds. The volume, which is the space, I'm going to circle volume and call that the space, must be no more than 8,000 cubic feet. A comparison of volume and weight. Here's a comparison I can use for you. Let's say we have this nice room we're in. Let's say we decide we're going to fill this room with packing peanuts. Do they weigh a lot? No, but we're going to fill it to the top. University's not going to be too happy, and it's going to weigh something, but it wouldn't weigh as much as, say, let's say we decide we're going to fill this room to the top with bricks. Both the bricks and the packing peanuts take the same amount of space, but their weights are very different. So volume is about the space that's available. To answer the question, I'm going to go with some of these questions that kind of walk you through things you need to pull out of the problem. The resources, this is the weight that the airplane can hold, and then the volume is a resource. And the volume of the airplane. The two products, this is what we want to ship. This is the food and the clothes. I called it recipes, but the recipes are the volume for the food and the weight of the food, and the volume for the clothes and the weight of the clothes. So the food, as I look at my problem again, each 20 cubic foot box of food weighs 40 pounds. I'm going to write the pounds first. 40 pounds for food and 20 cubic feet. For the clothes, each 5 cubic foot box of clothing weighs 20 pounds. So 20 pounds and 5 cubic feet. We want to know how many people are helped with each. So they told us each carton of food helps 14 people. Each carton of clothes helps 6 people. We are interested in finding how many cartons of each so that we help the most number of people. What are we being asked to find? How many cartons of food and how many cartons of clothes to send. I'm going to say this, the cartons of food, we'll let that be X, and the cartons of clothes, we'll let that be Y. So whatever they're asking you to find, that's the X and the Y. Well, in terms of how much to send, sometimes the problem might say, how many people were helped? That's a different question. We'll answer both on this one, but we'll look and see what they're asking us to type in. From these questions, I'm going to fill in the linear programming chart. These 4 boxes are about the recipes. The food weighs 40 pounds and it takes up 20 cubic feet. The clothing weighs 20 pounds and it takes up 5 cubic feet. There are some limits on the airplane. The weight limit is 23,000 pounds and the volume limit is 8,000 cubic feet. I'll fill in the people helped next. So the food helps 14 people and the clothing helps 6 people. Food is X, clothing is Y. So in the column for food, 40 times X, 20 times X, 14 times X. See, if I sent 10 boxes of food, I help 14 times 10, 140 people. So that's the multiplication here. We're sending X boxes, multiply. Do the same with the Y's. 20Y, 5Y, 6Y. The 2 constraints, you read the weight line straight across, put a plus sign in between 40X and 20Y, and put less than or equal to 23,000. So 40X plus 20Y is less than or equal to 23,000. For the cubic feet available, same thing. 20X plus 5Y is less than or equal to 8,000. The objective function is Z equals 14X plus 6Y to give me the total number of people helped.